Before we get to the example we are going to talk about, let's talk about a way to check whether a function is 1, 1 or 1, 2 graphically. For that, we have a famous test which you might have come across in the book Bartlett and Sherbert, Introduction to Real Analysis by Bartlett and Sherbert, or many other books in your undergraduation. So, horizontal line test is fairly easy. It helps us determine whether a function is 1, 1 or 1, 2. What you do is, you take a horizontal line, that is a line parallel to x-axis, and you move it around. When you move it around, if it, wherever you place that line, which is horizontal, if it cuts the graph at least once, throughout your real line that you consider. Here g is a function from r to r given by g of x equal to x. So throughout the real line, if the line touches the graph at least once, then it is a onto function. Now, if the line touches the graph exactly once, then it will be a one-to-one function. So if the line touches the graph exactly once, it's a one-to-one function, and if the line touches the graph at least once, it's onto. So we can find whether it's onto and whether it's one-to-one using horizontal line test. So moving the horizontal line will tell us that. Here clearly the line touches the graph at least once, and in fact exactly once. So g of x is equal to x is clearly a one-to-one and onto function, or 1-1 correspondence. Now let's consider g of x is equal to x square. Now when I move the line below x-axis, that is for y is equal to negative number, the line doesn't touch our graph. Therefore we can conclude that this is not an onto function. Now if I move it above x-axis, it touches the graph, but there's a small problem. It touches the graph at 2 points, not once. Hence we cannot say that it is one-to-one. So it's not an onto or one-to-one function when we consider our domain to be R and codomain to be R again. Going forward, let's consider the same function, but with another domain. Domain is going to be R itself, and codomain is going to be closed interval 0, infinity. In this case, when you here your codomain is going to be closed interval 0, infinity. Therefore, you start moving your horizontal line only from 0. Now, when you're moving up, you can see that it touches the graph at least once. Therefore, no matter how high you take, it touches the graph at least once. Therefore, we can say that this particular function g is onto, but it touches the at some point, except at line on x-axis, the x-axis line. At every other point, it touches the graph at more than one point. Therefore, it's not 1, 1. So with horizontal line test, simply we could conclude that g of x is equal to x square from R to close interval 0, infinity is onto but not 1, 1. We change the domain here. Now let's take a look at the definition of homeomorphism. In homeomorphism's definition, it is said that a function f is a homeomorphism if 1. F is if it's a bijection, and 2. F is continuous, and 3. F inverse is continuous. So if f is a bijection, f is continuous, and if inverse is continuous, then we call it a homeomorphism between two topological spaces x and y. With a small note, let's take a look at some examples. Now let's consider an example for homeomorphism. This function f is defined from open interval -1, 1 to r, and it is given by x by 1 minus x square. So Here, let's check if it's bijective. How do we check if it's bijective? We run a horizontal line all through the space, all through parallel to x-axis, all through our graph, and then we can see that the horizontal lines cuts the graph, and in fact cuts the graph exactly once in the entire breadth of r or y-axis. Therefore, we can say that this particular function cuts the graph, hence it's onto. It cuts exactly once, hence it's 1, 1 and onto. So by horizontal line test, we concluded that it's 1, 1 and onto, or it's a bijection. Now, if you look at the graph with the intuitive idea of continuity that was mentioned earlier, you can see that it is a continuous graph. Though it goes very steep at a point, it is very much continuous, and you can drive safely on this particular road. Therefore, this is f is continuous and it is a bijection map. Now, all that is left to check is whether f inverse is continuous. The inverse of this particular function is given by f inverse of x is equal to 2x divided by 1 plus 4x square to the power 0.5, or root of 1 plus 4x square. Now, obvious question is whether it is a bijection. It is known that if f is a bijection, f inverse will be a function and it will be a bijection. But still, if you are doubtful, you can always run your horizontal line throughout the space and see that it intersects the function graph of the function once and exactly at one point, all through the codomain. That is, here f is a function from open interval minus 1 comma 1 to r. F inverse will be a function from r to minus 1 comma 1. So that's settled. That should not be a question, because if f is a bijective, then so should it be f inverse. Now, is f inverse continuous? You can look at the graph and easily find out that f inverse is a continuous function, because it doesn't have any holes, or it doesn't have any jumping. It's not jumping up, or it's not dropping to infinity or rising to infinity all of a sudden out of nowhere. So therefore, we can say that this particular function is continuous, and hence f is bijective, f inverse is continuous, and f is continuous. Therefore, this is a homeomorphism from open interval minus 1 comma 1 to r.